Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be looking at numerical solutions to differential equations. In Chapter 1.4, we are introduced to numerical solutions to differential equations. This is especially useful when analytic solutions, algebraic solutions, cannot be found. We will present two methods, Euler's method and modified Euler's method. While these two methods are crude by modern standards, they do illustrate the basic ideas behind numerical solutions. An entire field of mathematics, called numerical analysis, deals with approximating solutions. In future courses, you will look at more robust numerical methods such as the Runge-Kutta method and the Doorman-Prince method. This set of guided notes will prepare you for the Euler Lab that you will complete in Microsoft Excel for your assignment on this section. You can reference Chapter 1.4 for additional resources, but the lab will be your homework assignment. Let's begin by looking at Euler's method. Given an initial value problem, y prime equals f of ty, y of 0 is equal to y naught. We know a solution must pass through the point 0, y naught. This is our initial condition. If we wanted to draw a solution to the initial value problem, we could follow this procedure. To start, draw a short line segment from the point y of 0 is equal to y naught here, using y prime to calculate the slope of the tangent line. Of course, the tangent line, or linearization that we called it in Calc 1, will generally only approximate the solution for y of t for a short time because the function y of t is probably not a straight line, as shown in Figure 1. So, after a short step in time of distance h, we will stop moving along the tangent line t naught at the point hy1. So here you'll see if you move a horizontal distance h, you'll stop moving on your tangent line t naught to this point hy1. From here, we will reevaluate the direction of the solution curve by evaluating the derivative at hy1. To find the slope of the tangent line t1, as shown in Figure 2. After a short step in time of distance h, which is here, we will stop moving along the tangent line t1 at the point 2hy2, because we are now 2 step sizes over, so our x value, our t value is now 2h. From here, we will reevaluate the direction of a solution curve by evaluating the derivative y prime at 2hy2. To find the slope of the tangent line t2, this line. This process will continue as we create a sequence of approximations of the solution curve of y of t. algebraically, Euler's method can be derived as follows. Given an initial value problem of the form y prime equals f of ty, y of t naught is y naught, Euler's method approximates the derivative at t naught y naught with the average rate of change which should look like your slope formula. That's the average rate of change between 2 points. With this approximation, the formula for y prime becomes, and here I'm manipulating this equation, where we're replacing y prime with the average rate of change. If we solve for y1, and to solve for y1, what I'm going to do is multiply to get the t1 minus t naught on the right-hand side. And then we're going to add the y naught to get it on the right-hand side. So this gives us a way to find y1. Finally, we let h be t1 minus t naught. Here. We refer to this as the step size. Then we obtain an equation for y1 from only the initial point t naught y naught. Similarly, we could represent y2 as follows. When this process is iterated, repeated over and over, we get similar equations for y3, y4, y5, and so forth. The general formula for Euler's method is written to find approximations for y of n plus 1, based only on the point that came before it, tn, yn. So here our yn plus 1 is calculated based only on what you knew at the previous point, tn, yn. A second method we can use to approximate solutions of differential equations is referred to as modified Euler's method. Euler's method can be made more accurate by averaging the slopes between two successive iterations. While I will give a short visualization of modified Euler's method here, I have also posted two fantastic videos by Houston Math Prep in our Canvas course under the Euler Lab module that illustrates both Euler's method and modified Euler's method. You should really watch these. They are great videos. Let's look at a visualization of modified Euler's method, though. So here we have the slope at t naught y naught as f of t naught y naught. So given this point here, we can approximate the slope or the tangent line to t1, y1. To find the slope at t1, y1, we must recall that we found y1 using Euler's method as y1 is equal to y naught plus h times f of t naught y naught. So the slope at t1, y1 here would be f of t1, y1, or f of t1 y naught plus h f of t naught y naught. Now what we would like to see from Euler's method, or modified Euler's method, is that the original slope we found at t naught y naught extends in this direction. And the slope at t1, y1 might extend back in this direction as well. What we would like to do is average these two slopes. So the average of these two slopes would be pretty much in the middle. And what we are going to find is that the average slope will provide a better estimate for T1. So to show you that, let's start from T naught, Y naught. Which is here. And rather than moving along T1, our first tangent line, we're going to move in the direction of our average slope, which should probably be moving in about this direction. So what we'd like to see that if we start at T naught here and we move over a step H, to T1, we are trying to approximate the Y value at T1. So here, Euler's method provides this approximation for Y1, while modified Euler's method provides this approximation, which is really close to the exact value of our Y value on our solution. So visually, we can see that the modified Euler's method does a better approximation for T1. So using the average of these two slopes, using the average of these slopes at these points will give a better approximation to the curve. Thus, modified Euler's method for finding y1 can be written as y1 is equal to y naught plus h, your step size, times the average of the slope at your first point and your second point. Where I'm going to rewrite the y value of the second point as y naught plus h times t naught y naught, because that's how we found y1 using Euler's method. In general, y of n plus 1, so your next point, is going to be found by looking at yn, your initial point, plus the average of, or plus h times the average of your slopes at tn, yn, tn plus 1, yn plus 1. Now, this algorithm is commonly written in two parts to simplify the calculation. First, we calculate un plus 1. Now, un plus 1 is just this y value. This is our un plus 1. This is our second point that we use. So we'll calculate that as un plus 1. We then perform the second step that uses the average slope between tn, yn, and tn plus 1, un plus 1 to compute yn plus 1, where this yn plus 1 is our yn plus 1, not from Euler's method, but from modified Euler's method. Okay, I hope this makes sense so far. I'd like to look at an example with you so you can see how these calculations are performed. So let's see. Use Euler's method to approximate the solution to the initial value problem. Y prime is equal to y plus 1. Y of 0 is equal to 1. With a step size of 0.5. We will do the first couple computations by hand. We will then use the power of Microsoft Excel to increase our efficiency. So replacing t and yn in Euler's method with y plus 1 and h with 0.5 gives the following. So here we have our general formula for Euler's method. And we're going to replace our step size and the expression for f of tn yn. Remember, this is the derivative. Remember, the derivative tells us the slope of our tangent line. So to use our formula, we'll create our first iteration by letting n equal 0. If n is equal to 0, then we're going to have y1 is equal to, if n is 0, y0 plus 0.5 times, if n is 0, this is going to be y0 plus 1. Where y0 is found from our initial value problem. This is y0 here, our initial y value. So 1 plus 0.5 times 1 plus 1. And if you simplify this, you should get 2. This is going to give our first point that we can plot, which is going to be at your t value of 0.5, because you did one step. And your y value is going to be 2. So specifically, I can label this as our t1, y1 value. Okay. If we continue to get our next iteration, we're going to be letting n equals 1. Now, if n equals 1 here, then we're going to have y2. If n is 1, this is going to be y1 plus 0.5. Again, if n is 1, this is going to be y1 plus 1. However, from our previous iteration, we know y1 is 2. So let's replace our y1s with 2, which will give us 2 plus 0.5 times 2 plus 1. I think if you simplify this, you should get 3.5. Which should give us our second point that we can plot. Now remember, if we're taking a step size of 0.5, then we're going to add 0.5 to our previous value to get to a t value of 1, and our y value is going to be 3.5. Where this is going to be t2, and this is now going to be y2. Now I'd like to give you a minute to do the next iteration on your own. So if you could, please pause the video and look for your next approximation where n is equal to 2. I will see you in a moment after you do these calculations. Okay, let's see how you did. If n is equal to 2, then we grab our formula for Euler's method. If n is equal to 2, then we're going to be calculating y3. If n is equal to 2, then we're going to start at our point y2 plus our step size 0.5 times, again, if n is equal to 2, this will be y2 plus 1. Again, from our previous calculations, though, we know y2 is 3.5. So let's replace our y2s, our previous point, to have 3.5 plus your step size times your 3.5 plus 1. Because I hope you simplified this expression, and you get 5.75. This gives us our third point that we can plot, which would be, first remember, our t values, we're taking steps of a half. So our next t value is going to be 1.5. And our y value here is 5.75. And again, specifically, this is the point T3, Y3. Now, I would like to compare this with our exact solution to this differential equation. And so let's take a moment and find our exact solution. So here I want to solve the initial value problem. Y prime is equal to y plus 1. Y of 0 is equal to 1. I'm going to do that on the next page so I can save some writing room here. So if we go to the next page, let's find our exact solution. Now, this should be a problem that you should be familiar with. So if we think about this differential equation, you want to recognize that this is a first order linear differential equation. And there's probably more than one method we could use to apply this, but I want you to recognize that this dE is a separable dE. You could also, so I want to use separation of variables. However, you could also use the integrating factor technique. That's up to you. But I'm going to use the separation of variables technique for solving this differential equation. Now, since this is a technique you're familiar with, you may want to pause the video and work this on your own for a little bit of self-practice. So if you could pause the video, work your solution to this IVP on your own, and come back and check and see if we get the same solution when you're done. I'll see you in a moment. Okay, I hope you paused the video. Let's see how we did. So let's start with rewriting the left-hand side as dy dt is going to equal to y plus 1. And to separate the variables, you want to divide both sides by y plus 1 to get it on the left. And then multiply to get dt on the right. This should give us dy over y plus 1 equals dt. At which point we choose to integrate both sides of the differential equation. Of course, on the left, this is technically a U substitution problem, but I think of this very similarly to the integral of 1 over x dx, which we know is just the natural log of x. So the similarity makes me think this left-hand side is going to be the natural log of the absolute value of y plus 1. Of course, there is some constant of integration here. If you'd like to check yourself, this would be a great point to take your derivative. Remember, the derivative of natural log of anything is 1 over this anything, times by the chain rule, the derivative of the anything, which is 1. And that should produce your previous integrand. The right-hand side, the integral of dt is just going to be t plus some constant of integration. Now, I'm not sure why I decided to write both these constants, because from our previous work, we know we're going to combine these two constants right away. So maybe I should have just written my solution as natural log y plus 1 equals t plus c. Now, at this point, I would like to solve for y. So we choose to exponentiate both sides of our equation with base e. Remember, when we raise the right-hand side with base e, both terms are in the exponent. Of course, on the left-hand side, the exponential and the logarithm will cancel, so just get the opposite value of y plus 1. On the right-hand side, again, you probably rewrote this as e to the t times e to the c. So you could write your solution as c e to the t. From our past arguments, we know that this absolute value can be sucked up by the constant. And so that if we solve this for y, we get y of t is c e to the t minus 1. We had the initial value problem, though, that y of 0 was 1, so let's find our constant c. We know y of 0 is going to be c e to the 0 minus 1, and this has to be equal to 1, which should tell us c is equal to 2. So we get 2e to the t minus 1. This is the solution to our IVP. 2e to the t minus 1. So I want to take this solution back to our previous calculations we were doing. And I wanted to compare our Euler's method approximations with the exact solution, which we just found to be y of t equals 2e to the t minus 1. Now, observe that in general, we may not know how to find the exact solution. So we should write maybe a little note to ourselves. In practice, the exact solution would not be known. And so that's why we were using Euler's method, is to approximate what this solution might look like. But as we're starting to build confidence in our skills, I want to have the exact solution as a comparison. So here now, I want to see how well did Euler approximate what is happening at t of 0.5. So let's look at the exact solution at 0.5. So if you evaluate your exact solution at t of 0.5, we should get, I think this, if I go to 2 decimal places, 2.29. Which is not exactly equal to our Euler approximation that we had of 2, but it's close. Now maybe we're expecting it not to be exactly the same, because let me scroll back again. When we thought of Euler's method, we approximated y1 to be here using our tangent line, which was different than what the actual value might have been, because we used a linearization. Okay, so if we continue, at our second iteration, we approximated y to be 3.5 versus the exact answer. Now here we're looking for the exact answer at t equals 1. And I'm going to round this to 2 decimal places again. You should get 4.44. At our next iteration, we predicted our y value to be about 5.75 versus the exact solution. Again, we're using t of 1.5. So when you plug 1.5 into your exact solution, and I'm going to round this again to 2 decimal places, I get 7.96. So what I'm noticing is that Euler's method is starting to diverge or differ from the exact value by quite a bit more as time goes on than it did initially. Let's look at this graphically, though. So let's first graph our exact solution. Remember, our exact solution started at the initial value problem. Y of 0 is 1, so here. Our exact solution at 0.5 was about 2.29, so maybe about here. At 1, it was at 4.44, so right here roughly. At 1.5, it was 7.96, so maybe about here. And a solution curve going through these points. Might look something like this. Of course, this would continue on, but this is what our exact solution would look like. Now let's also graph our Euler approximation. Now again, the Euler approximation started at the same initial value problem. So y of 0 is 1. At our first iteration, 0.5, we said the y value was approximately 2, so a little bit less. At 1, we said it was 3.5. So about here. At 1.5, we said it was 5.75. So roughly here. And let's draw a solution curve that would go through these points. And this would be our Euler approximation to the solution. Now, graphically, it looks like it's doing a pretty good job. However, what we should notice is that there is an error that seems to be growing between our exact solution and our Euler approximation. Now, in a more advanced course, you will look at error analysis. However, since this is our first look at numerical methods, I'm just going to reference that we do observe that an error is appearing. Now, as we've done these first 3 iterations by hand, we should acknowledge that there is a fair amount of work here. And in practice, nobody does this by hand. So what I would like to do is now talk about how we might use the power of Microsoft Excel to increase our efficiency in numerical calculations or numerical computations of solutions to differential equations. But I would like to do this in a separate video where I can go through the Microsoft Excel method for doing this. So I'm going to stop this video here. I'm going to create 2 more videos, one to show you how you might use Excel to approximate solutions of Euler's method, and then a second video for looking at the modified Euler's method that we presented earlier. So I'll see you then.